All right, let's see if we can do this. I would like to talk to you about how to do a serial dilution calculation. It is one of the things that microbiology labs involve, and you're going to use a serial dilution to do your standard plate count experiment. So there is a page in your course pack, page 56, which has an example of a serial dilution, which is worked out for you. But students often have trouble understanding the calculations unless someone goes through them. So I'm going to go through them with you right now. You'll have some practice calculations to do that are on page 57, I think, the following page that you'll be turning in for some points. Sorry, the example I'm going to do with you is on page 55, and the practice ones you'll do will be on page 56 in the course pack. So I'm going to share the example on my screen without the problems worked out. You have them worked out in your course pack, but I'm just going to talk you through where all the numbers come from, the calculations, remind you of a few things about working with powers of 10 that you do need to know for serial dilution problems. So the setup here is that we have our original material, the pond water, which is always going to be defined as having a dilution factor of 1. I'm going to write that here. Because we'll need that to get started. The other thing you need to know to do serial dilution problems is how you calculate the dilution for each container. And the pattern's the same for every container. So we're going to say that the dilution for any of the containers can be calculated with this same formula, which is it's the dilution factor for container N, where N could be A or B or C or D or E. It's like a variable in algebra. That's calculated by taking the dilution of the container right before it, multiplying by the volume that you're putting into container N, and then dividing that, dividing that by the total volume that you end up with in N. Now let's take a look at the dilution series, and you'll see the pattern here is a little complicated because we wanted to go through all the different sorts of dilutions that we normally do in a microbiology lab semester. So the original material, the pond water, we take 1 milliliter of that pond water and we add it to 99 milliliters of sterile liquid. That makes the dilution we're going to call dilution A. After mixing the tube A, we take 1 milliliter out of tube A and put it into the next container, which we call dilution B. And that container only has 9 milliliters of sterile liquid in it to start with, but we're adding 1 more, so it ends up with 10 milliliters. After we mix that dilution B tube, we remove 5 milliliters from that tube and add it to 45 milliliters of sterile liquid to make dilution C. Then 1/10 of a milliliter, 0.1 is 1/10 of a milliliter, is added to 9.9 milliliters of sterile broth to make dilution D. And then the final dilution, one takes 1 milliliter from tube D and adds it to 9 milliliters of sterile water in a new tube, and that makes dilution E. It's called a serial dilution because it is a series of containers where each tube has less and less of the original substance. All right, to the calculations now. So for container A, to figure out the dilution factor for container A, we have to know the dilution of the container right in front of it, which is the pond water. And we said the our original stuff, whether it's pond water or something else, we always define that as having a dilution factor of 1. So that's where that first 1 comes from. We're going to then multiply that dilution of the original by how much of the original we're putting into this container. So we're putting 1 milliliter of the pond water into container A. So that's where this 1 comes from. That's the 1 milliliter that's being added to the tube. We now have to divide that by the total volume of liquid in that container once we've added the pond water. Since there was 99 milliliters of sterile liquid to start, and we added 1 milliliter of the pond water, 99 plus 1 equals 100. Just want to remind you about how to express numbers as powers of 10. When you have a number of 10 or greater, it can be expressed as a positive exponent of 10. So just the number 10 is 10 to the first power. 100 is 10 to the second power. 1,000, 10 to the third power, and so on. So the way to figure out what your exponent is when you have a positive power of 10 is it's just going to be the number of zeros after the 1. So 10 has 1 0 after the 1, so it's 10 to the first power. This has 2 zeros, so we're going to be able to rewrite that 100 as 10 to the second power. And I'm going to superscript that. So we're farther along. We have our dilution factor for container A is going to be 1 over 10 to the second power. We would rather not write it as a fraction. We'd rather just write it as a straight exponent. And you can do that when you have a power of 10 on the bottom of a fraction. You can easily just convert that to a power of 10 by changing the sign of the exponent. In this case, the power of 10 on the bottom of the fraction is a positive number, plus 2. So, but we can turn that into, instead of 1 over 10 to the second power, we can write this as 10 to the negative 2. And that's the same number as 1 over 10 to the second. And that is the form we want our dilution factor in. So we can take this dilution factor of container A and use that to start to calculate the dilution of the next container. Okay, so we're going to take this 10 to the negative 2 and carry it down here. I'm going to not highlight it because it's not our answer here, but that's our starting point for calculating the dilution of the next container. So we have the dilution of container B is going to be calculated by taking the dilution factor of the previous container, which was 10 to the negative 2. And then to do container B, we need to take the volume of A that we're putting into B. It's 1 again, so that's where this 1 comes from. And then we're going to divide by the total volume that's going to be in this container. We start with 9 milliliters, we're adding 1 more. So instead of having 100 on the bottom of this fraction, it's going to be a 10 on the bottom. 9 plus 1 equals 10. Okay, so remember what I said about a positive numbers, 10 or greater, we can rewrite them as exponents. So we would rewrite 10 as 10 to the first power. Don't really have to do that, but it makes it maybe a little easier to see what you're doing here. So we've got 10 to the negative 2. That was times 10 1 over 10. But we said that's the same thing as 10 to the negative 2 times 1 over 10 to the first power. Once again, I don't really want this fraction. So I'm going to change the sign of the exponents and not have it as a fraction anymore and say that this is the same as 10 to the negative 2 times 10, what am I going to have to do to the 1? I have to change the sign. So instead of 1 over 10 to the positive 1, I'm going to say that's the same as just 10 to the negative 1. Here's one other thing you need to know about working with powers of 10. It's very, very easy to multiply powers of 10. So that's good news in terms of serial dilutions in microbiology, that we like to work with numbers in powers of 10, because if you need to multiply them together, it's a piece of cake. So how do we do that? We have exponents here and here. So we have 10 to the negative second, we have 10 to the negative first, and to multiply the two, 10 to the negative 2 and 10 to the negative 1, to multiply them together, what we have to do is we just add those exponents. So -1 plus -2 equals -3. That's how we got our dilution for container B. We take this, which was the final dilution factor for container B, and we're going to use this as our starting point for calculating container C. Okay, so container C is actually a sort of dilution you won't do in this class, but we do cover it. If you understand how to calculate serial dilutions, this shouldn't be too hard, and you do it in some classes. So here, to get container C, we're taking 5 milliliters from the previous container. So the volume we're putting into C is 5. That's where this 5 comes from. We then divide by the total volume in this container. It had 45 milliliters of sterile liquid. We're adding 5 more. So that gives us a total volume of 50 milliliters in container C once we've added the new stuff. Okay, so once again, we've got 10 to the negative 3. I'm going to carry that forward, but I want to work on that 5 over 50 fraction. Probably the simplest thing I can do is to simplify it by just dividing the top and the bottom of the fraction both by 5. So 5 divided by 5 is 1, and 50 divided by 5 is 10. You can do that with fractions. You can divide the top and the bottom. As long as you're dividing them both by the same number, you're not changing the value of the fraction. Okay, so this is starting to look more familiar again. We've got 10 to the -3 here from our previous container, carried forward. And this time, we're once again, we're dividing that, reducing it again by a factor of 1 over 10, or 10 to the negative 1. And then that gets us to a final dilution factor for this container. I'll let you think about it for a second, but it's 10 to the -3 plus 10 to the -1 will give you your exponent. So this is going to have a dilution factor of 10 to the negative 4. That's the final dilution factor for container C. We're going to take that as our starting point for the next container. That's what you always do with a serial dilution. So then we're going to multiply for container D. Let's see, what are we putting into container D? We're putting in less liquid. We're putting in only 1/10 of a milliliter, or 10 to the -1 milliliters. That's the same as 1/10. And our total volume in container D will be 9.9 milliliters plus 0.1. So that's just 10 to the first power. 10 milliliters is what we end up with in the bottom there. So that's a little different. We'll often do a 0.1 into 9.9 dilution in our class because we have a heck of a lot more test tubes that will hold 10 milliliters. Then we do flasks that will hold 100 milliliters. And really, a 0.1 into 9.9 dilution reduces your concentration exactly the same amount as if we did 1 milliliter into 99 milliliters of liquid, just in a smaller container. All right, so to fix this up, to make it easier to see what's happening, what I would do is I would take that 0.1 over 10 and I would multiply the top and the bottom of the fraction both by the same number, which is going to be 10. So 0.1 times 10 equals 1. If I multiply the top of the fraction by 10, I have to multiply the number on the bottom by 10 as well. So I have 0.1 times 10 is 1, and then I have to divide by 10 times 10. So I'm going to end up with 100 down there on the bottom, which I would rather write as a power of 10. Remember that 100, a 1 with 2 zeros after it, we saw in dilution A that if you have 100, we can rewrite that as 10 to the second power. And now we're all set to take that 10 to the second power from the bottom of the fraction to the top. We'll rewrite this as 10 to the negative 4 times, and now instead of saying it's times 1 over 10 to the second, we're going to say that's just the same as being times 10 to the negative second. That gives us a final dilution factor for this container of 10 to what? Okay, we have 10 to the negative 4 times 10 to the negative 2. What we do with exponents, when we multiply powers of 10, we just add the exponents together. So minus 2 plus minus 4 gives us final dilution here of 10 to the minus 6. We're going to carry that 10 to the minus 6 down to be our starting point for calculating the dilution factor of the last container in the series. And this will be easy. It's like the first one. Usually with most dilution series, if you can get the first and the second containers, dilution factors figured out, there will be a pattern that makes the rest of it a lot easier. You'll see that on the first of your practice questions on the following page that you'll do for lab points. Okay, so we've got our 10 to the minus 6, which we got as the final dilution of container D. We're going to use that final dilution of container D to figure the dilution factor for container E. So with container E, we started with a 10 to the minus 6 dilution of D, and we take 1 milliliter of that, so that's our 1 right here, 1 milliliter from the previous container. We're putting it into a total volume here of 9 plus 1. 9 plus 1 is 10. Let's say 10 to the first power. When you do a lot of serial dilutions and calculations like this, you quickly get to the point where you realize that 1 over 10 is the same as 10 to the negative 1. So you're probably getting close to that, and you will be closer by the time you do your practice dilution series on the following page. Okay, so we're going to say that that's the same as 10 to the negative 6 times 10 to the negative first power. Because 1 over 10 to the first is the same as just 10 to the negative first. To multiply 10 to the negative 6 and 10 to the negative 1, just like we always do when we're multiplying powers of 10, we take the two exponents, add them together. Minus 6 plus minus 1 gives us 10 to the minus 7 as our final dilution factor for our last tube. So there you go. You will check to see if you've got a handle on this by doing the 2 dilution sets that are on the following page, which is page 56 in your course pack. The first dilution set on that page, it should be pretty simple to do. The second one is trickier. It has some of those 0.1 into 9.9 dilutions that we had as our example for container D over here. So when you get to those, don't panic, but you can come back and look at container D to get a pattern for how you handle those 0.1 into 9.9 dilutions. All right, I think that's it for the serial dilution calculations. Oh, I should say one other thing. There are other practice dilution sets on pages 58 and maybe 59. I don't need you to do those. If you can do the practice dilution sets just on that first page, you will be prepared for anything that we will ask you to do on the lab exam. All right, that's the end.